In this video, we'll talk about the error bound on alternating series. So the alternating series test will only tell us that an alternating series converges. It does not tell us what this series converges to. Which is an important thing to know about this test. Even though you might know it converges, you don't know what that limit actually is. But because of the rigid structure on alternating series, it actually gets pretty close to what it converges to and give us a way to approximate what it converges to using the partial sums. So here's the result that we have. So if S is the sum of the entire alternating series, so Bn is our positive decreasing sequence that converges to 0, which is required by the alternating series test, then what do we know? Well, first, we know that this series converges by alternating series test. But what else do we know beyond that? And if we let S capital N be the nth partial sum, so summing from 1 up to capital N of this series, then we know that the actual sum of the entire series minus this partial sum, that difference in absolute value is bounded by the first term that we leave off the series. Right, so the sum counts up to the -1 to the n minus 1 times b capital N. The next term that we would get is a b sub capital N plus 1. So that's the first term we're leaving off by this partial sum, and that is the bound we get on our error for this sum. So we take n terms, we know that our error is no more than the first term that we've left off of this. Now, why is this the case? Well, it goes back to the argument from before as to why these series converge, right? If I know that Bn is positive, decreasing, going to 0, and I'm hitting it with this alternating plus and minus 1 sign, then I know I'm bouncing up and down as I go throughout the series. So if I draw some axes here to represent this, if I'm tracking the partial sum, right, I get something like, here is my length of B1 that gets added. Then I'm going to subtract down the amount that is B2, B3 comes up here, and I bounce back and forth, eventually sort of converging to what this limit's going to be. But what do I know? Well, I know that every time I make a jump, that is the highest or lowest I can ever be because the Bn's are a decrease sequence, right? Once I get past B3, there is no way for me to cross this line again because B4 is going to be smaller than that, so it's going to step down some amount that's smaller than B3, so I can't hit the bottom line down here. And then B5 is even smaller than B4, so that cannot make it up to the top point here. And that will continue forever and ever. So it means that once I hit B3, I can never cross that line again, which means that if I look at the next step down, I will also never be below that line ever again. So the value S is going to have to live somewhere in this strip, which means it's within B4 of the value I'd get at B3. So because it has to live somewhere in that strip, S is somewhere in here, it has to be within that bound that I've constructed here. It can't be further away than the length of B4 because that would make it outside that range and has to be in that strip somewhere. So that gives you sort of an idea of why this error bound here has to be true. Let's see what this looks like in terms of some examples. So let's analyze the alternating series -1 to the n minus 1 over n. First of all, does it converge? What else do we know? And how close is S10 to the overall limit S? So in this case, we have a series of the form n equals 1 to infinity of -1 to the n minus 1 times a bn, where my bn here is 1 over n. This 1 over n is positive, it's decreasing, and it goes to 0. Therefore, this alternating series converges by the alternating series test. And furthermore, since the sum from 1 to infinity of 1 over n diverges, and that's the absolute value of this, so that's the bn term, we know this converges conditionally. Now, let's look at some of the first terms of this series to see what we can say about it. So I know that my first term, if I plug in n equals 1, I get -1 to the 0, which is positive 1, times b1, which is 1. So my series will start with 1, and then minus a half, plus a third, minus a fourth, and so on. So because the first term is 1, I know the limit cannot be bigger than 1. That's going to be the highest it ever can be. So I know that S is less than 1. It's also bigger than 0. It's going to be positive. By the second term, I now know that it can't be less than a half. So I know it's between 1/2 and 1. Now what about S10? How does S10 compare to S? Well, our corollary from today says that S minus S10 absolute value is less than B11. B11 is 1 over 11. That means that I know that S10 must be within 1 over 11 of the total series limit. If I wanted a force to be within, say, 1 over 1,000, I could take 1,000 terms and I would know for a fact that I'm then within 1,000 terms because this bound would tell me that. That's what we know about this series from this corollary and this setup here. Now to wrap up alternating series, we want to look at 2 examples and determine their convergence or divergence directly. So both of these are alternating series. The question is, do they converge or diverge? So for the first one, we have our Bn being n over root n squared plus 1. Now for this, if we look, we have a power n on top. We have really kind of a power n on the bottom. It's n squared under a square root, which means that this limit doesn't go to 0, right? Limit as n goes to infinity of Bn is 1, which is not 0. Therefore, the alternating series test does not apply. Now that on its own does not mean the series converges, diverges, doesn't mean anything. We have to look and find some other argument for why this series might converge or diverge. And the argument here comes from the nth term divergence test. So the fact that this Bn limit goes to 1 means that the limit as n goes to infinity of the entire term, negative 1 to the n times n over root n squared plus 1, this limit does not exist. Basically, the coefficient part here wants to go to 1, but then I'm getting plus and minus 1 alternating signs. So I'm having half the sequence go to plus 1, half go to minus 1. Therefore, this limit does not exist. So by the nth term divergence test, it diverges. That test, remember, says if the limit does not go to 0, the series must diverge. So this diverges by the nth term divergence test. What about the second one? The second one, what we had was our Bn was 1 over n log of n. Now in this case, this Bn is in fact positive, decreasing, and goes to 0. So therefore, we know that the alternating series converges by the alternating series test. To go beyond this, we want to see if it converges conditionally or absolutely. We can apply the integral test to the sequence Bn, which is 1 over n ln n, which will tell us this diverges. So that means that the entire thing converges conditionally. So that's it of using the error bound on alternating series to talk about what the limit should be, even if you can actually compute it directly from the alternating series test, as well as how you can look at a series and analyze whether it converges or diverges using any of these tests, including the alternating series test and the test developed previously.